We navigate our everyday lives using a mental yardstick built for borders, edges, and limits. But those internal measurements quickly reach their absolute limit when we try to calculate something that never ends. Think of a movie theater. If you walk in and see that every single seat is occupied by exactly one person, you know immediately the total number of seats and the total number of people are equal. But does that rule of one-to-one matching hold true if the rows of that theater stretch out forever? We also rely on density to judge amount. If you are driving down a dark highway and the streetlights spread further and further apart, your brain interprets that increasing rarity as a decrease in the total number of lights. But if that highway has no finish line, does a fading density actually result in a smaller total? Finally, we rely on the geometric rule of parts and wholes. If you take a photograph and physically slice off a corner, the severed piece is, by definition, smaller than the original picture. But what happens if you cut a piece out of a picture that has no edges? Can the severed piece ever be just as large as the whole? Pairing, density, and subsets. These three rules govern everything we touch in our finite reality. Yet when applied to the concept of infinity, they cease to function. In 1638, Galileo Galilei decided to test these exact boundaries. He realized that by observing simple numerical patterns, he could demonstrate that our basic assumptions about numbers were actually illusions. He looked at two specific groups of numbers. The first group was standard natural numbers, 1, 2, 3, 4, and so on. The second group was their perfect squares. This diagram shows the first 10 natural numbers. Within this specific group, only 3 of them, 1, 4, and 9, are perfect squares. Scale that view up to 100, and you only find 10 perfect squares. As the numbers grow larger, the squares become statistically rarer, leaving increasingly large gaps between them. This creates a cognitive trap. Because the perfect squares are a smaller subgroup, we instinctively conclude there are fewer of them. If we follow the rules of rarity and parts to wholes, the set of perfect squares appears vastly smaller than the set of all numbers. But let's go back to the movie theater. We have to apply the strict rule of one-to-one matching to these numbers. Take the very first natural number, 1, and multiply it by itself. It pairs with the square number 1. Continue the pattern in sequence. The natural number 2 generates the square 4. 3 generates 9. Now extrapolate this rule outward. Every imaginable natural number can be multiplied by itself to create a perfect square. The math leaves no gaps. No regular number lacks a square, and no square exists without its original natural root. This creates a logical deadlock. The squares appear to be rarer, yet the one-to-one pairing proves both sets possess the exact same quantity of elements. This mathematical contradiction is known as Galileo's paradox. Neither set is larger. Both sets are the same size. Galileo concluded that comparative words, concepts like larger, smaller, and equal, lose their meaning once you enter an endless domain. This reveals a core property of the infinite. An infinite proper subset can be the same size as the infinite superset it was cut from. Mathematics functions perfectly here. The friction comes from an intuition that evolved to handle finite things. Centuries later, mathematicians like George Cantor would formalize this, proving that both of these are countably infinite sets. Despite their deceptive appearance, they share the exact same cardinality. When we stare into the endless, a piece is just as large as the whole. At that scale, our